In the last video, we hopefully learned the intuition behind the ideal gas equation, that pressure times volume is equal to the number of molecules we have times some constant times the temperature. And that's all nice, and hopefully it makes sense to you how all of these fit together, that pressure should be inverse to volume, and that's why you're multiplying both sides, or that's why you're multiplying them by each other. You could take volume and put it on this side of the equation, or that pressure should be proportional to the number of particles and the temperature. But now let's apply it and actually do some problems, because just knowing this isn't good enough. So let's say that I have let me make up something good. Let's say that I have a 2-liter container, or let's say a 2-liter balloon. 2-liter balloon, not balloon. Balloon containing hydrogen gas, and that's hydrogen as a diatomic molecule. So each molecule has 2 hydrogens in it. And let's say I'm measuring it at 30 degrees Celsius. Let me do a different color. 30 degrees Celsius, not 30, my brain is really malfunctioning. 30 degrees, not 30%, 30 degrees Celsius. And let's say that we measured it to be, that the pressure on the outside of the balloon we've measured at 2 atmospheres. 2 atmospheres. So my question to you is, how many moles of hydrogen do we have? How many moles? How many moles? So let's apply our ideal gas equation. And since we're dealing with liters and atmospheres, we have to make sure we use the right proportionality constant. But in general, if we keep pressure, so our pressure is given in atmospheres. So let me write down all of the units actually. So we have 2 atmospheres. 2 atmospheres times our volume is 2 liters. 2 liters times 2 liters is equal to N. N is the number of particles we care about, right? And we care about it in moles, but let's just write N there for now, is equal to N times R. Times R. Now what R should we, well I'll do R in a second. Times R times T. Now, you might be tempted to just put 30 degrees in there, but in all of these problems, and in fact in general, whenever you're doing any of these gas problems or thermodynamics problems, or anytime you're doing math with temperature, you should always convert into Kelvin. And just as a bit of a review as to what Kelvin is, it's just a different scale. So for example, the lowest possible temperature that can be achieved in the universe, when you think about it in Celsius, let me draw a little temperature scale here. So if that's a temperature scale, I'll draw 2, one for Celsius and one for Kelvin. So the lowest possible temperature that can be achieved in the universe, excuse me, I know when I cough it tends to be a little jarring. And when we say the lowest possible temperature, that means that the average kinetic energy of the molecules or the atoms are 0. They're just not moving. They're just, they're just stationary. So it's very hard. So in Celsius, it's minus 273.15 degrees Celsius. So 0 might be someplace over here. 0, that's where water freezes, and then 100 degrees, that's where water boils. And you can immediately see Celsius was, the whole Celsius scale was made based on the freezing point and the boiling point of water. Now, Kelvin, but when you look at this and you say, oh, if I have something that's 5 degrees, and have another thing that's 10 degrees, when you look at the Celsius scale, you're like, oh, maybe the 10 degree thing, it has twice as much energy as the 5 degree thing. It has twice the temperature. But when you look at it from the absolute distance to 0, the 10 degrees is only, let me see if I can draw this. So the 10 degree is all the way over here, and the 5 degree is almost as far. It's that far. So the 10 degrees Celsius is only a slight increment over 5 degrees Celsius if you were to divide the two. It's not twice as hot. And that's why they came up with the Kelvin scale, because at the Kelvin scale, absolute 0 is defined as 0. 0 Kelvin. So this right here is 0 degrees Kelvin. And so 0 degrees Kelvin is absolute zero. So what's 0 degrees Celsius? Well, we would have, and the increments are the same. 1 degree change in Celsius is 1 degree change in Kelvin. So at least it's just a shift. So this is going to be plus 273 degrees Kelvin. And then 5 degrees would be plus 278. 10 degrees would be plus 283 Kelvin. And then you see that 5 and 10 degrees really aren't that different from each other. But in general, if you want to convert from Celsius to Kelvin, you just add 273 degrees. So 30 degrees Celsius is what? 30 degrees Celsius is, well, it's probably sitting, this 5 and 10 I drew too close to 100, but let's say it's sitting here. It would be 303 degrees Kelvin. So this is equal to 303 degrees Kelvin. Alright, so now for our temperature, that's what we were worried about. We wanted to put in the temperature there, so now we can put in our 303 degrees Kelvin. Now we have to figure out what unit, what constant to use here, and I've written a couple down here. Remember, we're dealing with atmospheres and liters. So I wrote down a couple of versions of R right here. Let's see, we're dealing with atmospheres and liters. The denominator, we're always dealing with mole and Kelvin, no matter what. So those are always going to be there. So we should use this proportionality constant. R is equal to 0.082 liter atmospheres per mole Kelvin. Let me write that down. So let me rewrite our whole equation actually. So I have 2 atmospheres. 2 atmospheres times 2 liters is equal to N times, I have a bad memory, 0.082 liter atmospheres per mole Kelvin times 303 degrees Kelvin. Alright, so let's see what we can do. Let's see if all of the units work out. So we can always, when you do dimensional analysis, you can treat units like numbers. So if you divide both sides of this equation by atmospheres, the atmospheres cancel out. Divide both sides of this equation by liters, liters cancel out. You have a Kelvin in the numerator, Kelvin in the denominator, that cancels out. And so we have 2 times 2 is equal to N times 0.082 times 303, and then we have just a per mole, and a 1 over mole. So to solve for N, or the number of moles, what we do is we divide both sides of this equation by all of this stuff, right? So we get, let me just write this, so we get 4, 2 times 2 is 4, 4 divided by 0.082 divided by 303. I'm just taking this and putting it on the left-hand side, dividing both sides by it. And when you divide by a per mole, if you put a 1 over a mole here, that's the same thing as multiplying by a mole. So moles is equal to N. So it's good. The units all worked out. We're getting N in terms of moles. And so we just have to get the calculator out and figure out how many moles we're dealing with. So we have 4 divided by 0.082 divided by 303 is equal to 0.16. If we wanted to go more digits, 0.161, but we'll just average round. So this is equal to 0.16 moles of H2. And if we wanted to know the exact, I mean, I am telling you actually here the exact number of molecules of hydrogen molecules. But if you wanted a number, you would just multiply this times 6.02 times 10 to the 23, and then you would have a number in kind of the traditional sense. And of course, if you wanted to know what is the mass of the hydrogen you have, you'd say, okay, well, 1 mole of H2 has a mass of what? So 1 molecule of H2, the mass of 1 hydrogen is 1 atomic mass unit. The mass of 2 hydrogens, when it's in its molecular form, is 2 atomic mass units. So a mole of it is going to be 2 grams, right? So in this case, we have 0.16 moles. So if we wanted to convert that to grams, well, I don't even have to use a calculator. This, in the case of hydrogen, of these hydrogen gas molecules, would be 0.32 grams. And I just multiplied it by 2 because each mole is 2 grams. Anyway, hopefully you found that useful. I'm going to do a bunch more of these problems because I think the math is pretty straightforward here. The thing that always makes it daunting, I think, is the units and making sure they're using the right units. What if they're using meters cubed instead of liters, or kilopascals instead of atmospheres? So I'll try to do a bunch of examples where we use all of the different units and we are able to pick our constants appropriately.